Ja, dann herzlich willkommen zum heutigen zweiten Vortrag. Der zweite Vortrag wird von Dr. Christian März gehalten. Herr März ist derzeit engagiert an der University of Leeds und er wird heute erzählen, The Past, Present and Future Diplom gemacht in Geologie, Paläontologie an der Universität Heidelberg und ist anschließend, wie Katrin vor ihm schon, an die Universität Bremen gewechselt und hat dort seinen Doktor gemacht in mariner Geochemie. Als Postdoc war er dann angestellt unter anderem an der Universität Oldenburg und an der Newcastle University. An der letzteren Lecturer, bis er 2016 zum Associate Professor in Biogeochemistry an der University of Leeds berufen wurde. Sein Forschungsschwerpunkt ist die anorganischen geochemischen Techniken zur Untersuchung von jurassischen bis modernen Sedimenten mit einem Schwerpunkt auf organikreichen Ablagerungen und subarktischen Umgebungen. Und einen Satz, den er mir noch zugespielt hat, den wollte ich euch nicht vorenthalten. Herr März spent almost a year in total at sea on various research ships. Das ist, glaube ich, das, was wir uns alle irgendwann mal wünschen nach dem Studium. But now spends way too much time on administration. Das ist das, was wir uns vielleicht nicht unbedingt alle wünschen. Und damit würde ich übergeben an Herrn März und freue mich auf den Vortrag.
Ja, vielen Dank für die Einladung und Einführung und auch nochmal vielen Dank für den vorherigen Vortrag von Katrin. Das ist wirklich ein spannendes Thema. Salinität ist ein Proxy, den haben wir wirklich noch überhaupt nicht im Griff. Und speziell in der Arktis spielt es auch wirklich eine große Rolle. Also es wäre sehr schön, wenn man da wirklich was entwickeln könnte, was ein bisschen besser funktioniert. Ja, ich gehe da mal ins Englische. So yeah, as Robin already indicated, today I'm probably mainly going to talk about the Arctic Ocean, an earth scientist perspective, just because I'm an earth scientist, so I studied geology and paleontology of all things. But then over time, I've really merged more into a marine biogeochemist. So this picture is just a little taste of what work in the Arctic Ocean can be like sometimes. So that's the lovely German icebreaker Polarstern in the background. And that was in 2008, my first expedition to the Arctic. So we were playing football with a basketball on the frozen Arctic Ocean. So that was relatively spectacular. Now, obviously, when you give a talk about something, you always want to give a bit of a background. Why do you do this type of research anyway? Well, for the Arctic Ocean, it's not particularly difficult because the Arctic Ocean is just an area that is undergoing such dramatic changes at the moment, as we probably all know. It's changing faster than the global average, and it's a process called Arctic amplification. It has a number of different reasons. And it's most significantly expressed in dramatic reductions in the thickness and the extent of sea ice on the Arctic Ocean. So the top left picture you can see here, the yellow line indicates the summer sea ice extent. Well, September, that's the minimum sea ice time in the Arctic for basically 30, 40 years prior to 2010 as an average. And then the white represents the September sea ice content in 2012. So that is currently the lowest sea ice extent we've recorded. But you can see on the lower graph that there is a very clear trend to continuously declining sea ice coverage in the Arctic Ocean, certainly over summer. Now, there are a number of reasons for that. One of the reasons is that the water that is entering the Arctic Ocean, both through the Fram Strait from the Atlantic and the Bering Strait from the Pacific, is also getting warmer. And this makes it more difficult for new ice to form in winter. So there is more melting in summer, less sea ice formation in winter. And one thing I just want to make very clear is that The melting of the sea ice has no direct effect on sea level, as you probably all know, because it's just floating on the ocean, but it makes the ocean darker. And if you've been in the Arctic Ocean, the contrast is stark. You see the white ice and the ocean looks black. So it has a very different albedo. It basically means it warms up. So the dark water warms up just by being dark. Now, the Arctic Ocean is not just an isolated ocean at the top of our world. It is also very critical in global climate. And Katrin showed this picture of the thermohaline circulation already. It basically is driven by processes, namely deep water formation in the North Atlantic. Now, if in the Arctic, for example, the Greenland ice sheet melts, that will introduce huge amounts of fresh water to the North Atlantic. That will make it much, much more difficult for deep water to form. Hence, the engine of this global oceanic conveyor belt will start to stutter a little bit. There have been various movies on this topic, basically Europe falling into a new ice age or something like that. But the weakening of the overturning circulation is a real thing. Now that's another thing that people are always really interested in and keen about, the ecosystems in the Arctic Ocean. Most importantly, of course, the polar bear. Everybody loves them, nice and fluffy. They are vicious predators, and I honestly don't know how they survive in such a harsh environment. It really is remarkable. But obviously they depend on a highly specialized ecosystem in the Arctic Ocean. And if warming continues, sea ice retreats, they have nowhere to go. There is no further north than the Arctic Ocean. So we will lose this unique ecosystem, and that would be a real shame. Now, there is also a more, I guess, anthropogenic interest in the Arctic Ocean, in that the Arctic Ocean offers very interesting alternative shipping routes if there is no sea ice in summer anymore. So the left-hand map here just shows a ship setting off in, let's say, Hamburg and going all the way to Japan. The blue route is the route the ships currently take. The red route is the Northeast Passage through the Siberian Arctic. So that would make the travel significantly shorter. This route is currently operated. So you can basically buy tickets to traverse the Northeast Passage, and then you line up with your ship behind a Russian nuclear icebreaker, and you just follow them. But it's very expensive, and it's not very, well, it doesn't make much sense at the moment. But shipping traffic in the Arctic is already increasing as sea ice is retreating. And then the right-hand map shows estimates by the US Geological Survey on hydrocarbon resources under the Arctic, so somewhere deep in the sediments. So there is quite an interest by the hydrocarbon industry in the Arctic Ocean. And I'm going to show some data from some of these very organic-rich deposits in the Arctic in a minute. There is interest. Some hydrocarbon companies have already ventured into the Arctic Ocean, but it still freezes over in winter, and it is dark all the time, so it's still a hostile environment. But countries like Russia and Norway, they are expanding further and further offshore. So they are watching the sea ice development very carefully as well. So really, the take-home point here is, in order to protect the Arctic Ocean, and I think it is worth protecting, we need to understand it. And one component of this understanding is geosciences or earth sciences. So looking at the bottom of the Arctic Ocean, not necessarily just at the ice or at the water column. Now, one might ask, why do we still know so little about the Arctic Ocean in comparison with other oceans? So I'm asking you this question. It is a fact. We know much less about the Arctic Ocean. Various reasons. It is obviously very difficult to access. You need icebreakers most of the time. It's a very hostile environment, so it's always cold. It's dark in winter, so any cruises only tend to go in the summertime. And then the Arctic Ocean is really complicated, geologically speaking. So we roughly know when it formed, in particular, the more European side of the Arctic Ocean, the Eurasian basin. It's basically an extension of the Atlantic Ocean. But for the Canadian side, we have not really any idea. And that's quite remarkable. I mean, it's an ocean that has been known for a long time, and we still don't really know how it formed. So I just love these artist illustrations of the seafloor, because they just highlight very nicely how complex the Arctic Ocean is. One thing to note here already is that the Arctic Ocean is surrounded by extensive shelf seas, and that's where a lot of the change we see is currently happening. So that's where the sea ice retreat is happening. Now, one question you might also ask about the past Arctic Ocean in particular is, looking at the Arctic Ocean now, it's ice covered, it's an oligotrophic system, so it's not very productive. You don't have enormous algal blooms or anything like that. So why is there so much oil and gas in the sediments at the bottom of the Arctic Ocean, which require the formation of source rocks, which are by definition organic rich rocks? So why is that the case? Well, the Arctic Ocean used to be a very different environment from what it is now. It used to be a highly productive marine setting. It was highly restricted as well, and you can see that on the right-hand map here. It's really just in the middle of this map, sitting there almost like a lake. It was warm. It was brackish. During certain times, you had a carpet of freshwater fern. So perfect preconditions for forming a hydrocarbon source rock. A lot of organic matter being produced, and the preservation conditions at the seafloor being really, really good. And this was the case during what we call a particularly strong greenhouse interval in Earth's history. So that is the Cretaceous to Eocene. That's also in one of the oxygen isotope stacks that Katrin showed. That's a period where globally temperatures were really high. So the Arctic Ocean was also surrounded by a lush vegetation. We know that from fossil findings. You had the weirdest mammals running around there. You had crocodiles, you had turtles. So it really was a completely different place from today. Now, how do we know that is the case? Well, I already told you, you find fossils in the deposits surrounding the Arctic Ocean, wherever they are cropping out. But we also look at the seafloor and take sediment cores from there. So as Katrin already said, these sediment cores we're taking are basically archives of mud accumulated over millions and millions of years. And getting this mud is never particularly easy, but in the Arctic Ocean it is particularly hard, and it's also very expensive. And this slide and the next slide, I'm going to talk mainly about the so-called Arctic coring expedition that was part of, well, what it's now called the International Ocean Discovery Program. It's been going for 50 years in various iterations. It's an international drilling program that operates a number of drill ships that drill really deep into the seafloor, in this case around 400 meters, very close to the North Pole. And it was an extremely expensive expedition because they had to take 3 icebreakers to the Lomonosov Ridge, which is this submarine ridge at the middle of the Arctic Ocean. I think some colleagues at NEOS, where Katrin is, were heavily involved in this expedition, and it's just worth Googling it. I think there are some really interesting videos of how they actually recovered these sediment cores. And this just brings me to generally work for a marine geoscience, or particularly marine geochem like mine is. So we tend to go on research, not just IOP expeditions, but also on research ships in national research fleets. So in Germany, we have Germany has a very good and well-maintained research fleet with a number of really great ships. You go to sea, you recover sediment cores. This is just an example of multi-cores. They are relatively short, but they preserve the sediment-water interface very nicely, which is important for certain types of research. You also can take much, much longer cores. One thing that almost everybody does is sampling the sediment. One thing that I tend to do, and not many other people, is extracting pore waters from these sediments. So that is the liquid that is stuck between the sediment grains. You can do it using a chemical squeezer that just squeezes the sediment together. That's the top image here. You use something like an artificial root. You just stick into the sediment, attach a syringe, and you pull out the water, and it comes out already filtered. Lovely. And then you analyze all your samples for various, in my case, geochemical parameters. Now, I want to show you a few examples of these sediment archives at the seafloor of the Arctic Ocean. This is an example of what sediments on the Arctic margins often tend to look like. Really colorful. You have these lovely brown layers that I'm going to talk about quite a lot. But just to say that these sediments are lovely natural archives of environmental change. And we use so-called proxies that Katrin was already introducing to basically translate the sediment record into meaningful information. Katrin is looking at salinity. I am looking at, for example, bottom water redox conditions, or I'm looking at bottom water energy, current velocity, you name it. There's a proxy for almost everything, but none of them are perfect. That's the real problem. So this is just another sediment core, and that relates back to this Arctic coring expedition very close to the North Pole. And that is basically an archive of how the Arctic Ocean looks like now and how the Arctic Ocean looked like during a greenhouse period. So you can see the sediments on the right-hand side. Well, you can hardly see them because they are so dark. So they are very rich in organic matter. They have a very good potential to develop into oil and gas source rocks. Currently, in this location, they are not cooked enough, so they aren't buried deep enough to actually express hydrocarbons. But those are, for example, some of the deposits that form hydrocarbons surrounding the Arctic Ocean, where burial rates are greater. And then you have this weird interval in between, which is also called the zebra interval. I'm not going to go into detail. It's really a weird interval. But then the younger sediments, which is kind of the most left panel in this figure, they tend to be grayish, brownish. They are in organic matter, but they have a lot of these lovely brown layers. So they represent the onset of the Ice Age world, when we had growing and shrinking ice sheets. While in the greenhouse world before, in the Cretaceous and Eocene, ice sheets were much, much smaller, if they even existed at all. So that's just a nice illustration of how this particular core, which is, by the way, the only sediment record we have from the central Arctic Ocean that goes back that deep and is more or less continuous, how you shifted from this greenhouse into this icehouse world in the Arctic Ocean. And these are just some wiggly lines that I love to produce based on my data, and they show how you can illustrate and extract certain information out of these very different types of deposits. So you see here a number of different chemical elements plotted against core depth, and these elements are silica, copper, and molybdenum. In this particular context, the silica is indicative for the abundance of biosiliceous plankton, mainly diatoms. And copper and molybdenum are so-called redox-sensitive elements. They tend to be enriched quite strongly if you have oxygen-depleted bottom water conditions. So what this shows is, in the red square, that's the greenhouse interval, you had a highly productive Arctic Ocean, lots of biosiliceous productivity. You had oxygen-depleted bottom waters, enrichment of trace metals, also of organic matter. And that's a situation not unlike some of the deep basins in the Baltic Sea at present. People often use the Black Sea, which is also a completely oxygen-depleted basin. But we found that the Arctic was probably more similar to what the Baltic looks like today. Anyway, you then enter into this green box and you see your sediments look much more boring. There's hardly anything going on. Also, organic carbon is really low. So that's your low productivity and well oxygenated Arctic Ocean that we've had for the last tens of millions of years, I would say. But this is basically how you can use sediment geochemistry to extract information out of the sediment cores, inorganic geochemistry, I should say. Now, one problem we have with all the proxies we are working with is we can never be 100% confident in them. And this is what Katrin's thesis is also all about, improving proxies we are using. Basically, like letters in a book convey information to those who can read, we read proxy records in the sediment and relate them to environmental parameters. But proxy records can change long after sediment deposition. And that is driven by biogeochemical processes that happen below the seafloor. Like text in a book can be modified. You know, you can change things, it can be translated, you lose information, information gets shifted around. Especially in books that are very, very old. So these biogeochemical processes in marine sediments or in lake sediments, they are termed early diagenesis. And they are all driven, and that is kind of shown on the left-hand side here, by the degradation of organic matter. It's the same thing that happens in your compost heap. You chuck your kitchen waste on there and microbes break it down and they extract nutrients from it. This is why compost is such a good fertilizer when you're doing any gardening. Now, in marine sediments, there is as you can see on the left-hand side here, quite a complex sequence of chemical reactions that happen. You don't need to understand any of the details. But one thing I want to point out is that the middle panel here shows the accumulation of certain elements in the pore waters, which, if you remember, is the stuff I extract from the sediments. Because from the pore waters, you get a lovely snapshot of what is currently going on in terms of organic matter degradation in the sediments. And that is really important to understand if you want to understand early diagenetic processes in the sediment and in how far they might be overprinting some of your paleo proxies. And in the next minutes, I'm going to talk about kind of a case example specifically in the Arctic Ocean. But basically, we need to understand early diagenesis because otherwise we'll create alternative facts in paleo-environmental reconstruction without noticing it really. So the example I want to talk about, and I'm going to try to keep this quite short, is Arctic manganese stratigraphy. So manganese is a chemical element. It behaves a little bit like iron. So for the Arctic Ocean, the idea was, well, we want to know what it looks like in the future when it's warmer. So let's look at sediments that were deposited when it was warmer than, well, the pre-industrial period, pre-Holocene. So interglacial periods, interstadial periods. Now, the problem in the Arctic Ocean is, and it's a very notorious problem, sediments in the Arctic Ocean are very difficult to date. Hardly any of the methods that are applied in other parts of the ocean work there, for a variety of reasons, but take my word for it, the age models are not particularly robust. So, and then people said, well, in the Arctic Ocean, you find these lovely brown layers and they seem to occur all around the Arctic margins. They seem to occur everywhere. So they must have a relationship to the paleo environment. And I'm not gonna go into detail of how that view was developed, but it was agreed basically for quite good reasons, I should say, that these brown layers represent warmer periods. Okay, that's perfect. We know from the global climate records, oxygen isotopes, for example, how many glaciations we had over the last 500,000 years. So why don't we just count these manganese layers in the cores and link them to each other, correlate them? Basically a chemostratigraphy. So marine geologists started counting manganese layers. And this started quite early on, already in the 80s. These brown beds were recognized, initial stratigraphies were being built up, supported by some other data. But then really in 2000, Martin Jakobsen and his colleagues from Stockholm, they developed for the first time a correlation of one particular sediment core in the Central Arctic Ocean to this, what you see on the left-hand side here. That is this global oxygen isotope stack that is basically the gold standard for dating and correlating any sediment cores to get age information. They also found that these brown layers are apparently very rich in manganese, specifically in manganese oxide. It's basically the same as rust, but instead of iron, it contains manganese. So they basically built the first link between the stratigraphy of sediment cores in all oceans with sediment cores from the Arctic Ocean. So hooray, really great achievement. But then already in the 1960s, some marine geochemists found, well, manganese is an element that is incredibly mobile during early diagenesis, which means in this particular case, and this is really a key paper, the left-hand side shows manganese in the solid phase in the sediment. The right-hand side shows it in the pore waters. So if you have manganese in the pore waters, it means it gets released from the solid phase and it is lost and redistributed, shifted up and down over meters, as you can see here. So you have a manganese peak in the sediment that is evidently dissolving, at some point might be completely gone, might be related to an interglacial. You wouldn't recognize that anymore. And a new manganese peak is forming. And that peak might be potentially forming in sediments that represent no interglacial, but now you have a manganese peak, so people would assume it's an interglacial. Tricky. Now, over the last 10 years, and I'm going to go through this quite quickly, I worked together quite a lot with colleagues in Stockholm, especially, but also really all over the world, to understand this manganese stratigraphy a bit better. So what we did was measure the chemical composition of the sediments, as we did here. You can see in this particular sediment core, lovely manganese peaks. Interestingly, these peaks are also rich in certain trace metals, molybdenum and cobalt. Now, the interesting bit is that the layers aren't equally enriched in manganese and cobalt all the time. Some layers are very rich in molybdenum, very poor in cobalt, or the other way around. And we're thinking, well, that's a bit odd. Because they both like to sorb to manganese oxides, why don't they behave in exactly the same way? The pore water data gave us an indication. You can see here this manganese profile, that's the second from the left. You have high concentration of manganese in the pore waters at depth, which means manganese is released from sediment into the pore waters, it's lost, and it diffuses through the sediment, forms a new manganese layer. Molybdenum is a metal that apparently also has the same diagenetic behavior. So it migrates together with the manganese. Cobalt, on the other hand, doesn't do much at all. So we thought, well, that's interesting. Cobalt doesn't get remobilized, molybdenum gets remobilized. Can we maybe use the relationship between those traces to understand better how strong manganese layers have been affected by diagenesis? Long and behold, this was mainly done by a PhD student in Oldenburg, Ann-Kathrin Meinhardt. She found that layers that have experienced a significant loss of manganese, so where a brown layer might have disappeared, they have a lot of cobalt and very little molybdenum. And if you have a layer that's newly formed in the sediment, without any relationship to climate, that has very high molybdenum and very low cobalt. So that's a nice chemical indicator. Works really well. But then we work together with the colleagues in Stockholm, as I indicated. What they do is they basically X-ray sediment cores. They do so-called radiographs, and they are like a visual description, but they highlight density differences very nicely. And what you can see in this middle panel is an example of a layer that geochemically we've found is a diagenetic layer, and you can see it looks very particular. It has these, like almost finger-like, we say, dendritic growth of manganese in the sediments. If you've ever worked in the Solnhofener Plattenschiefer, that's something you tend to find in there as well on a much bigger scale. On the other hand, the layers that were formed near the sediment water interface, so at the seafloor, so probably related to climatic conditions, and that's what you see on the right side here, they are pervasively bioturbated. They don't show the structure like in the middle panel at all. So there's also a visual way of distinguishing these layers from each other. So that was a really nice collaboration. That's really taken us further in terms of understanding these manganese cycles. So just to summarize that bit of my talk, these layers are well known. Some are related to warmer conditions. Others are purely formed by early diagenesis. And there are certain conditions that make that more likely. Both processes aren't mutually exclusive. In all likelihood, in any sediment core, you have manganese layers that are related to warm periods, and you have a diagenetic overprint. The question is, how strong is that diagenetic overprint? But basically, our understanding of how geochemical proxies work, or generally how any proxy works, is continuously improving, and it usually has something to do with people from different subdisciplines in geosciences talking to each other and not digging themselves into trenches and saying, what you do is wrong, what you do is wrong. It's just a more of a philosophical statement, really. Always try to collaborate with other people. Now, last bit of my talk, a slightly different flavor. And I want to lead into it by asking a kind of, well, challenging question. Greenhouse gas levels are currently increasing, so will the Arctic Ocean switch back to being a highly productive and oxygen-free and, of course, ice-free environment like we saw in the last greenhouse period? There are some arguments that we are moving into that direction. And to basically understand a bit better how the Arctic Ocean is currently, before our own eyes, changing, I got involved most recently into a big research project in the frame of this so-called Changing Arctic Ocean program. That's a big program mainly funded by the UK, but there's now also co-funding. Oh, sorry, my daughter just came home. I'm just going to shut the door. Sorry about that. At least one person misses me. So this research project program, the Changing Arctic Ocean, was funded mainly by the UK, but there are quite a few projects co-funded by the Bundesministerium für Bildung und Forschung as well. So it's also a partly German initiative. And it's all about understanding how current changes in the Arctic Ocean are impacting its biology and biogeochemistry. And I had a project that was called, well, I led a project called CHAOS, the Changing Arctic Ocean Seafloor, because I'm a geologist. And I said, we can't ignore the seafloor. It's an ecosystem, it's a habitat, it's a biogeochemical reactor. We want to understand that as well. We had 3 cruises to the Barents Sea, which you can see here on the right-hand side, just north of Norway. On this lovely ship, you can see on the left-hand side, the James Clark Ross. It's now gone out of service and is being replaced by Boaty McBoatface, the Sir David Attenborough. And it's an enormous project, this CHAOS project. It's very interdisciplinary. This is just really a part of the team. So we had microbiologists, benthic ecologists, we had modelers, organic, inorganic geochemists. It's a great project, and it's just terminated, and there's still great things coming out of it. But within this project, one of the things that I was particularly interested in was in how far does the Arctic Ocean, and particularly Arctic shelf sediments, act as a carbon sink? If productivity is increasing, might that also translate into an increase of organic carbon burial in the sediments, removing excess CO2 from the ocean atmosphere system? So we looked at the carbon cycle. Not important. Yeah, this is just a little bit of statistics. What did we actually analyze? Well, we had these different sampling locations in the Barents Sea. We basically only looked at muddy sediments because the sandy ones or gravelly ones, they are just extremely hard to recover. So we're missing a bit of the picture, but that's one of the intrinsic issues with marine geosciences. You can only study what you can actually sample. Yeah, we had a great team on board. It was always great fun. almost everybody manages to dab. So one thing that we studied in particular in Leeds, and that's kind of the last bit of my talk, is the so-called rusty carbon sink. And that's quite a cool thing. So that basically means the preservation of organic matter in association with iron oxides, effectively rust. So what did we do? We took some sediment cores again, we sliced them up. Most of this work was being done by Johann Faust, who is wearing this white hard hat. And we extracted the pore waters using these rhizons in quite high resolution from our little poor junkie cores. And the thing we studied is something that some of you might have seen if you have a cast iron pan and you don't really pay attention. Very often they have a rusty button and they are also sooty, so have a lot of carbon like ruß on it. This association between carbon and iron also exists in nature, and that was found in 2012 by this pioneering study by Karine Lalonde and others. They basically said that between 10 and 30% of all the organic carbon in surface sediments worldwide, so really just at the seafloor, is associated with iron oxides. And there is a general assumption that that stabilizes the organic matter. It's less prone to be degraded by microbes, which means it's easier to get buried and removed from the ocean and from the atmosphere over long time scales. It was found that that is also the case in Arctic surface sediments. That's this top right plot here. But one thing we were interested in was how stable is this rusty carbon sink? Because as I already said, there is early diagenesis going on. Iron oxides tend to get dissolved and degraded, just as manganese oxide. So that would release the associated organic matter. And this is, by the way, just showing how this association might look like. So you have a core of iron oxides, and then either you have organic carbon around these iron oxides just adsorbed. We don't really know that, or it co-precipitates. So you precipitate a bit of iron oxide, so it's basically a closer chemical association between both elements. Now we wanted to study, again using pore water and sediment data, does this association between iron and carbon survive early diagenesis? Long and behold, yes, it does to a great extent. So this is the team that mainly worked on this, Johan, Ellie, and Ben. And this is just one of the sediment cores we looked at. You can basically see in this red circle, that's the fraction of organic carbon that is bound to iron oxides. And you can see it decreases down core slightly, but it doesn't disappear. Although we know there is a lot of iron oxide dissolution going on. We know that from the pore water iron profile here in orange. So we know that these sediments in the Barents Sea are thousands of years old. So this rusty carbon sink seems to survive this diagenetic processing, which is good news because that increases its potential to draw down carbon from the atmosphere. Is there maybe a geoengineering thing in here? Who knows? We are just really beginning to understand this association in real terms. But basically, this takes me to the end of my talk. So as we heard in the first bit, the Arctic Ocean used to be much, much warmer, but that is a long, long time ago. So to anyone who tells you, well, it was much warmer, does it matter? Well, the whole world was a very different place back then, and probably not very, not necessarily a nice place to live in. Very muggy. The Arctic Ocean is drastically changing. We don't really understand how it's changing and how fast it's changing. It's basically changing too fast for us to do all the studies we need to do. We need very interdisciplinary understand the whole Arctic Ocean, includes the seafloor. And the seafloor in this context is, yes, a recorder of past climatic conditions. So it tells us about past warm periods, but it's also a biogeochemical reactor. You have diagenesis, you need to recognize that. And it is a very important burial ground for carbon. And this is a function that we need to understand much, much better to see how the Arctic Ocean might actually be a solution rather than a victim of modern climate change. And that's me. Thank you very much.
Ja, vielen, vielen Dank für diesen wirklich spannenden und ich glaube auch sehr wichtigen Vortrag. Die Änderungen, die gerade da im arktischen Ozean ablaufen, die werden ja mit Sicherheit auch Auswirkungen auf unser Leben haben. Und genau da hatte ich auch eine Frage. Die Auswirkungen, oder die Veränderungen, was könnten die bei uns bewirken? Und sind das wir, die das noch mitbekommen, oder sind das dann schon unsere Kinder? Kann man sowas schon abschätzen?
Also abschätzen kann man alles. Ne? Modellierer würden jetzt sagen, ja, modellieren kann man alles, aber die sagen einem da auch, alle Modelle sind falsch, aber manche Modelle sind nützlich. Es gibt eine Sache, die oft irgendwie angebracht wird, vor allem von Meteorologen, ist, ja, verstärkter Schneefall im Winter, vor allem hier in den, ja, England, Deutschland, das hat was mit der Meereisbedeckung zu tun. Das verschiebt irgendwie den Jetstream. Da gibt es zwei komplett unterschiedliche Ansichten. Manche Leute sagen, das ist so, das können wir auch belegen. Andere Leute sagen, Atmosphärensystem ist derartig chaotisch, das werden wir vielleicht nie verstehen. Das ist allerdings was, also ich meine, man sieht, dass das Klima weltweit, sagen wir mal, instabiler wird. Inwieweit das jetzt allein vom arktischen Ozean gesteuert ist schwer zu sagen, aber wenn ich mir vorstelle, dass man quasi eine vorher komplett weiße Fläche in jetzt eine komplett schwarze Fläche umwandelt, das muss sich irgendwie auf die Zirkulationssysteme auswirken. Und die Zirkulationssysteme sind eben irgendwie verbunden. Da bin ich kein Experte, aber so relativ naiv, würde ich mal sagen. Das muss Auswirkungen haben. Naja, und dann dieses Abreißen des Golfstroms oder die Schwächung des Golfstroms. Ich glaube, das ist tatsächlich über die letzten Jahrzehnte schon gesehen worden. Ob das plötzlich irgendwann drastisch abreißt, schwierig. Aber eine Sache ist klar, die Eisschilde weltweit, also auf dem Land, Grönland und die Antarktis, die stehen höchstwahrscheinlich nur ein paar Jahrzehnte vor irgendwelchen Tipping Points. Das bedeutet zum Beispiel, dass bestimmte, ja, es gibt da so Eisshelves. Da liegt das Eisschild, also das Eisschild liegt quasi da so schön auf Meeresboden aus. Und dann schiebt der komplette Eispanzer den jetzt freien Eisschelf nach draußen. Und da ist quasi eine Bremse gelöst. Dann schmelzen die, rutschen diese Eisschilde viel, viel schneller ins Meer. Das ist in der Tat problematisch. Und das ist momentan noch sehr schwer abzuschätzen. Ja, man muss einfach viel mehr Forschung machen. Wie immer.
Ja, vielen Dank. Ich sehe, das ist die erste Frage von Carsten.
Ja, genau. Erstmal vielen Dank für den netten Vortrag. Ich hatte noch eine Frage, was die Wasserstoffisotopie anbelangt, weil wenn man Redox-Bedingungen hat, die viel organisches Material bindet, müsste man dadurch nicht auch Wasserstoff versenken oder verliert man die Signatur durch Diagenese oder Redox-Bedingungen wieder?
Wasserstoffisotope jetzt im Porenwasser oder im organischen Material selber?
Ja, ob man das nicht auch dann als Proxy benutzen könnte.
Ja, es ist immer die Frage, worin man Wasserstoffisotope misst. Also was Katrin macht, die in ganz speziellen organischen Molekülen zu messen, das ist mit Sicherheit eine gute Möglichkeit. Und inwieweit das von diagenetischen Prozessen überprägt wird, ich meine, der Proxy ist erst in der Entwicklung, von daher möglicherweise nicht, möglicherweise schon. Ansonsten, ja, Wasserstoffisotope, also die werden generell viel benutzt, um den hydrologischen Kreislauf, also den Wasserkreislauf ganz generell zu rekonstruieren. Also ist tatsächlich hauptsächlich ein Proxy für Regenfall, Flusswassereintrag. Da gibt es bestimmt noch viel Potenzial. Es ist nur so, dass ja, speziell in diesen ganzen alten Sedimenten, die sind vielleicht noch keine Kohlenwasserstoff produzierenden Sedimente, aber die sind schon wärmer, als sie ursprünglich mal waren. Das ist nicht unbedingt Frühdiagenese, das ist eher so mehr thermische Reifung, die vielleicht die organische Substanz und vor allem die molekulare Zusammensetzung beeinflusst haben könnte. Ich weiß also nicht genau, wie viel da noch möglich ist. In jüngeren Sedimenten vermutlich schon.
Ja, okay, vielen Dank.
Ja, Katrin schrieb gerade, Wasserstoffisotope in Komponenten recht stabil sind und wenig ausgetauscht. Ja, das ist gut. Das ist doch. Haben wir noch eine Antwort von der Expertin direkt?
Genau, vielen Dank nochmal an Katrin an der Stelle. Gibt es denn weitere Fragen? Sonst hätte ich vielleicht noch eine. Diese Brown Beds. Ich weiß, dass es in der deutschen Nordsee die weichselzeitlichen Sedimente, die wurden früher dort auch immer als brauner Sand bezeichnet, zumindest in der deutschsprachigen Literatur. Und heute wird es so gedeutet, dass die quasi im frühen Holozän dann, teilweise unter bodenbildenden Prozessen, dann diese braune Einfärbung bekommen haben. Kann man das dann so stehen lassen oder müsste man mit dem neuen Wissen das vielleicht auch nochmal speziell darauf untersuchen?
Naja, ich denke mal, die Braunfärbung, dass das bodenbildende Prozesse sind, basiert nicht alleine auf der Braunfärbung oder dass die vielleicht jetzt reich an irgendwelchen Eisen- oder Manganoxiden sind. Also ich denke, es ist höchst selten, zum Glück, dass Geowissenschaftler sich nur auf ein Proxyfold verlassen. Es ist immer so ein, was man so als Multi-Proxy-Approach bezeichnet. Und speziell bei diesen Ablagerungen diesen glazialen Ablagerungen in Norddeutschland, ich glaube, die sind rauf und runter untersucht. Also da kann man wahrscheinlich relativ sicher sein. Vor allem sind die Sedimente wahrscheinlich gar nicht mehr so sehr wassergesättigt. Es können immer noch gewisse diagenetische Überprägungen stattfinden. Es ist tatsächlich auch so, was ich jetzt von marinen Sedimenten erzählt habe, läuft in allen Böden genauso ab. Und das ist auch der Grund dafür, dass zum Beispiel irgendwelche Braunerden oder so hauptsächlich an der Oberfläche, wo oxidische Bedingungen herrschen, so eine braune Lage haben. Marine Sedimente weltweit haben das auch. Das ist einfach wirklich Umverteilung von Eisen, von tieferen Lagen, direkt an die Oberfläche, wo du wieder Sauerstoff hast. Das sieht man im Wattenmeer auch ganz schön zum Beispiel.
Ja, vielen Dank. Wenn jetzt keine weiteren Fragen mehr kommen, dann würde ich mich nochmal recht herzlich bedanken bei Ihnen, Herrn März, und auch nochmal bei Katrin für diese zwei wirklich spannenden Vorträge heute. Und ja, entlasse damit alle anderen und wünsche noch einen schönen Abend.
Ja, ebenso.